Welcome to the Deep Dive, where we tear apart vast stacks of source material, sift through the noise, and extract the brilliant, indispensable nuggets of knowledge you need to be truly well-informed.
Today, we are focusing on a man who, in many ways, defined the intellectual chaos and eventual triumph of the scientific revolution, Johannes Kepler.
Kepler is a name everyone remembers from high school science, usually followed by the phrase, planets move in ellipses.
Right. And if that's all you know, you've missed a monumental intellectual story.
Yeah.
The man wasn't just a brilliant geometrician. He was a German astronomer, a physicist before physics even really existed, an astrologer, an optical theorist.
A philosopher whose greatest desire was to reveal the actual mind of God through mathematics.
Exactly.
When you look at his full biography, you realize he wasn't just a stargazer. He was a true polymath operating at the precise intersection of old-world mysticism and modern empiricism.
And his work solidified his place as one of the fundamental founders of modern astronomy, the scientific method, and, well, natural science itself.
And he even dabbled in early science fiction with his novel Somnium. We have to talk about that later.
Oh, we will. Our mission today is to understand how this seemingly contradictory blend of geometry, theology, and rigorous physical curiosity led him to establish the foundation of modern celestial mechanics.
And all this despite a life that was just plagued by personal tragedy, relentless religious conflict, and perennial poverty.
And this is where the intellectual paradox of the early 17th century comes into sharp relief.
You mean the split between astronomy and physics?
Yes. Before Kepler, the universe was conceptually bifurcated. Astronomy was mathematics. It was purely about geometric models for predicting where planets would be. It had nothing to say about why.
It was descriptive, not explanatory.
Precisely. Physics, or natural philosophy, was about explaining the causes of motion forces, matter, mechanism. It was grounded in Aristotelian ideals.
And Kepler just smashed those two together.
He fundamentally broke that division. He described his revolutionary work not as pure astronomy, but as celestial physics.
The celestial physics, I love that term.
He was the first to propose that astronomical phenomena must be governed by universal physical causes, integrating math and mechanism into one single system. This quest for the physical motor of the cosmos, the why, is what pushed him past everyone else.
Okay, so let's unpack the difficult beginnings of this revolutionary thinker. Kepler was born in 1571 in the free imperial city of Wilderstadt,
Which is near Stuttgart. And here's a piece of context that really it defines his entire life.
the religious tension.
Right. Even though his family was staunchly Lutheran, the sources note he was presumed baptized Catholic
Why?
because Protestant baptisms weren't legally permitted there at the time.
Wow. So right from birth, he's caught in the middle.
It's a powerful illustration of the religious volatility in the Holy Roman Empire, a volatility that would eventually lead to the 30 Years' War and directly impact Kepler's own survival.
And his childhood environment was chaotic, not just religiously, but economically too.
Yeah, his grandfather had been a Lord Mayor, so there was some status there once.
But the family fortunes had completely collapsed by the time he was born.
And his immediate family life was hardly stable. His father, Heinrich, was a mercenary.
The mercenary.
He left when Johannes was only 5, just abandoned the family, and was eventually believed to have died fighting in the 80 Years' War in the Netherlands.
And his mother, Katharina Guldenman, was a healer and an herbalist.
Which, as we'll tragically see later, was a profoundly risky occupation in that era.
So we have to pause here for a moment on the sheer irony of the physical circumstances of this future master precision.
It's unbelievable. Kepler was born prematurely, and he claimed throughout his life to be weak and sickly.
And worst of all, childhood smallpox left him with weak vision and crippled hands.
Think about that. The man who would redefine observational astronomy was physically unsuited for it.
He couldn't really do the observations himself.
Not well. It made him entirely reliant on the data collected by others, specifically Tycho Brahe.
Yet the intellectual curiosity burned bright. Even as a child, his phenomenal mathematical faculty impressed travelers at his grandfather's inn.
And he had those two foundational astronomical moments that cemented his life path.
The Great Comet.
Yes, the Great Comet of 1577, which he observed at the age of 6, and then a lunar eclipse at age 9.
Which he described vividly, right? He remembered how the moon appeared quite red.
These were direct, visceral experiences with the heavens that deeply moved him and, set him on his professional course.
But his formal education was initially aimed at the pulpit.
Right. He attended the Tübinger Stift at the University of Tübingen to train as a Lutheran pastor. And this is where he met Michael Maestlin.
And Maestlin taught him both systems, the traditional Ptolemaic geocentric model and the newer radical Copernican heliocentric system.
And Kepler didn't just accept Copernicanism. He became its passionate defender.
And critically, he defended it on theological grounds as well as mathematical ones.
That's the key. He believed that the sun, positioned at the physical center of the universe, was the principal source of motive power.
For him, the cosmos was an image of God.
Exactly. The sun represented the Father, and therefore it logically belonged in the central position of influence. This belief that he was uncovering God's geometric plan was his lifelong driving force.
But this deep conviction cost him his intended career.
It did. His theological position ran counter to the strict Lutheran formula of Concord, which was the statement of faith adopted in 1577 that sought to unify Lutheran doctrine.
So his independent thought was a problem.
A huge problem. He was subsequently denied ordination as a minister because his personal beliefs were considered unacceptable to the Orthodox Lutheran establishment.
So in 1594, he accepts a teaching position instead.
And heads to Graz in Styria as a teacher of mathematics and astronomy at the Protestant school.
His time in Graz, though short, was essential for building his reputation.
It was. He enhanced his status by issuing the standard official calendars and prognostications, fulfilling the duties of an astrologer.
Even though he felt conflicted about it.
He often did, especially about the vague nature of many astrological practices of the time.
And this was also a time of personal growth. He married Barbara Miller,
A twice-widowed heiress. And the sources highlight that their engagement was nearly derailed due to Kepler's extreme poverty.
That's a recurring theme, isn't it? His money troubles.
Always. But he eventually secured the match.
And the real intellectual splash came in 1596 with the publication of Mysterium Cosmographicum.
The cosmographic mystery.
This is the ultimate example of Kepler trying to impose mystical, perfect geometry onto the heavens.
Oh, absolutely. He theorized that the spacing of the 6 known planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, was perfectly explained by nesting the 5 Platonic solids within spheres.
The Platonic solids, so the octahedron, icosahedron, dodecahedron, tetrahedron, and cube.
The 5 perfect geometric shapes.
Yeah.
He believed that if you stacked them and drew spheres around and within them, the spheres would correspond exactly to the 6 planetary orbits.
He saw this as the ultimate proof that the Creator had used pure, crystalline geometry to construct the cosmos.
Yeah.
So wait, if the data he had access to, primarily Copernican, was already known to be slightly inaccurate, why did he cling so fiercely to this model?
It wasn't just geometry. For him, it was theology.
I see.
He believed geometry was the visible expression of God's eternal thought. For Kepler, if the Platonic solids didn't work, it meant the Creator was arbitrary, which was just unthinkable.
So the book established his reputation.
It did. But it simultaneously forced him to acknowledge that the available data, the Copernican numbers, didn't quite match his beautiful theory.
The mismatch was slight.
But enough to bother a mathematician of his caliber. He realized he needed observational data that was orders of magnitude better.
And just as the scientific need became paramount, the political hammer fell.
Growing religious tension in Graz Protestant enclave under the Catholic Habsburg rule of Archduke Ferdinand II led to a decree ordering all Protestant preachers and teachers to leave.
That was in September 1598.
Yes. And although Kepler initially received a special exemption, he was uneasy. He knew his security was temporary.
And that drove him to seek powerful new patronage.
His sights immediately fell upon the one man who had the data he needed, Tycho Brahe.
The most accurate observational astronomer who had ever lived.
So Kepler set off to Bohemia in January 1600. And when he finally met Tycho at Banatki nad Jezeru, the initial encounter was famously tense.
It almost ended their collaboration before it began.
Tycho Brahe was a lord of his own intellectual manner. He had spent decades collecting this massive, incredibly precise data set, and he guarded it like dragon's gold.
He was impressed by Kepler's theoretical brilliance, though.
Oh, for sure, especially the Mysterium Cosmographicum. But he was a notoriously difficult and controlling personality. The sources tell us that negotiations for employment broke down in an angry argument.
Because Tycho wouldn't release all his data at once.
Exactly.
A personality clash between two giants, but thankfully, they reconciled quickly.
Good thing, too, because in July 1600, a new, harsher decree was announced in Graz, forcing all Protestant inhabitants to renounce their faith or leave.
And Kepler's temporary exemption was revoked.
He was forced to leave in September 1600, cementing his complete reliance on Tycho's patronage and the security of the imperial court in Prague.
So he arrives there, essentially fleeing persecution, and finds himself dependent on the difficult generosity of Tycho, ready to tackle the greatest problem in astronomy.
The orbit of Mars.
So once Kepler arrived in Prague, he was immediately put to work as Tycho's assistant.
And Tycho, knowing just how complex it was, assigned him the most notoriously difficult problem: deciphering the path of Mars.
Mars has the most eccentric or non-circular orbit among the naked eye planets.
Right, and Tycho had observed it with unbelievable precision. This task was the crucible of Kepler's career.
And then, suddenly, just 2 days after Tycho's unexpected death in October 1601,
Kepler was appointed his successor as Imperial Mathematician to Emperor Rudolf II.
a high honor, but immense pressure.
Pressure and continuous financial strain. The emperor's court was magnificent, but his overextended imperial treasury meant that Kepler was constantly owed back pay.
That financial desperation fueled his need for side work and eventually drove him to his death.
Yeah. He was required to provide astrological advice, which he did with skeptical precision, but his true focus was scientific. These 11 years in Prague were arguably the most scientifically productive of the entire scientific revolution.
We see that independence immediately with the supernova of 1604, or SN 1604.
Kepler systematically observed this bright new star that appeared in the evening sky.
And this was a colossal moment for cosmology.
It was, and he captured it in his treatise De Stella Nova. Because Tycho's data was so accurate, Kepler could prove that the star exhibited no measurable parallax,
Meaning it had to be impossibly distant.
far beyond the planetary orbits and the supposed immutable sphere of the fixed stars.
Why does that matter so much?
It shattered the Aristotelian doctrine that the heavens were perfect and unchanging.
Right.
The birth of a new star implied change, variability, imperfection. It extended the terrestrial rules of birth and decay to the celestial realm.
It was a conceptual step that prepared the intellectual ground for his later, more radical theories.
Exactly.
Okay, now let's dedicate the necessary time to the masterpiece, Astronomia Nova, New Astronomy, published in 1609.
Kepler spent years trying to fit Tycho's observations of Mars to a perfect circle, the standard geometric model inherited from the Greeks.
And this is where the famous 8 arc minutes discrepancy comes in.
Yes. After painstakingly calculating Mars's position over time, Kepler found that his best circular model disagreed with Tycho's observations by 8 minutes of arc.
And that is a tiny amount, about a quarter the width of the moon as seen from Earth.
Microscopic. But it became the monumental scientific failure that catalyzed a revolution.
Because anyone else would have just ignored it.
Earlier astronomers, using less accurate tools, would have fudged the data or blamed observational error. But Kepler knew the rigor of Tycho's work.
He famously declared, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly."
But he couldn't. He knew those 8 minutes were God's challenge to him.
So he was forced to toss out the concept of the perfect circle.
And in doing so, he tossed out the rigid structure of 2 millennia of astronomy. He rejected the old idea of a planetary orb, a physical, crystalline sphere carrying the planet.
And he replaced it with the idea of a planetary orbit.
A mathematical path traced out in space that resulted from physical causes.
This was the radical shift to celestial physics. He was no longer just drawing circles, he was asking what force kept the planet moving.
And what force did he propose?
He was heavily influenced by William Gilbert's 1600 treatise De Magnete.
Right. Kepler surmised that the sun acted as a giant magnetic dynamo, radiating a motive power. Motrix-like magnetic spokes across the solar system.
And he reasoned this power weakened with distance.
Following some kind of inverse relationship. This sounds almost mystical, but it was a crucial, necessary step.
Even if the mechanism, magnetic spokes, was physically incorrect, it established the principle of physics governing the heavens.
Exactly. It provided the physical basis for his laws. This weakening force was the physical explanation for why planets moved faster when closer to the sun and slower when farther away.
So he had to find a geometric way to represent this variable speed.
Which was computationally excruciating, was monstrously complex.
To simplify the calculation, he reformulated the relationship geometrically.
Yes. In late 1602, he discovered his most elegant simplification, Kepler's second law.
The area law.
A planet sweeps out equal areas in equal intervals of time.
That law essentially solved the variable speed problem and made prediction possible again. But the geometric shape of the path was still wrong.
He was still trying to fit the data to an ovoid, or egg-shaped curve, which was closer to the data but not quite right.
The sources show the intensity of this struggle. He tried over 40 different geometrical hypotheses.
It was a mathematical war of attrition. He even tried to define the path using epicycles centered on the sun. Everything failed to resolve those 8 arc minutes.
And then the final breakthrough moment in late 1604, he discovered the perfect curve,
The ellipse.
Kepler's first law.
He concluded that all planets move in elliptical orbits, with the sun situated at one of the 2 foci.
And the historical irony is that he had actually encountered the ellipse earlier in his calculations, but had discarded it.
He believed it was too simple a solution for earlier Greek astronomers to have missed. His mind, driven by the geometric complexity of the Platonic solids, resisted the mathematical simplicity of the ellipse.
So the man who spent his life chasing perfect, divine geometry ultimately had to accept the slightly imperfect but physically accurate geometry of the ellipse.
Driven by the undeniable empirical data. Precisely. His religious drive for perfection forced him to become the ultimate empiricist.
And it's vital to understand that he did not extend the mathematical analysis beyond Mars at that time because of the immense calculation involved.
But he was confident, based on his magnetic fourth rationale, that the law was universal.
The manuscript was complete in 1604, but publication was held up until 1609.
Because of legal disputes with Tycho's heirs who claimed ownership of the observations.
Which just shows how essential Tycho's data was. Kepler needed legal permission to use the physical proof of his laws.
A decade later, Kepler attempted to unify and disseminate his system in the Epitome of Copernican Astronomy.
Published in 3 volumes between 1618 and 1621.
And this was crucial because it explicitly stated that the first 2 laws applied universally to all planets, the Moon and the newly discovered satellites of Jupiter.
Galileo's Medicean satellites.
Yes. Unfortunately, the timing was terrible.
The Catholic Church had already placed Copernican books on the Index of Forbidden Books.
And the growing tensions that would lead to the 30 Years' War made printing and distribution fraught with danger.
But once it started circulating, the Epitome became the ultimate vehicle for spreading Kepler's ideas.
It was the standard textbook between 1630 and 1650, moving the entire astronomical community toward ellipse-based physical astronomy.
The move from Prague to Linz in 1612 marked a new phase, driven by profound personal loss.
His first wife, Barbara, died from Hungarian spotted fever, and one of their sons, Friedrich, died from smallpox.
So he took the position of district mathematician in Linz, Austria, while keeping his Imperial Mathematician title.
Though the pay remained sporadic, of course.
And in an almost tragically systematic way, following Barbara's death, Kepler spent 2 years meticulously researching and considering 11 different prospective matches for a new wife.
This process has been noted by historians as an early real-world example of what mathematicians later called the secretary problem.
Or optimal stopping problem.
Yes.
So the man who mapped the perfect cosmic architecture couldn't even manage a simple courtship without treating it like a mathematical optimization problem.
Essentially, yes. He documented the pros and cons of each candidate based on their background, demeanor, financial standing, everything.
And he eventually chose Susanna Reitinger.
The 5th match on his list. He praised her for qualities like humble loyalty, economy of household diligence, and the love she gave the stepchildren.
Sources suggest this was a far calmer and happier marriage than his first.
It seemed so, but the personal calm was immediately countered by religious turbulence.
While he was working in Linz, which had a strong Lutheran presence, his own local pastor refused him communion.
This was due to his prior religious nonconformity. He was excommunicated because he refused to fully endorse the strict Lutheran formula of Concord.
Specifically, he disagreed with the doctrine of ubiquity.
The theological belief in the real presence of Christ's body and blood in the Eucharist everywhere. Kepler's adherence to physical reasoning led him to reject this literal interpretation.
That seems like an intensely specific theological point to lose your standing over.
It was. His appeal to the Stuttgart consistory failed, and his excommunication was unequivocally declared in 1619.
And this is why historians call him a super-confessional Lutheran.
The man whose allegiance was ultimately to the truth he could derive, whether scientific or spiritual, rather than to strict denominational dogma.
He famously advocated for tolerance, stating, "Christ the Lord neither was, nor is Lutheran, nor Calvinist, nor Papist."
A radical statement for the time.
But the personal strife escalated dramatically into something terrifying in 1615, the witchcraft trial of his mother, Katharina.
She was accused by Ursula Reinbold, and quickly other rumors, fueled by her status as a healer, began to circulate.
This was a life-and-death ordeal.
Absolutely. Kepler was completely dedicated to defending her, viewing the trial as an attack on his family and perhaps indirectly on himself.
Because of his own unpopular doctrinal stance.
Exactly. He spent years providing legal aid, writing defenses, and traveling back to Württemberg during a period of immense political instability.
And Katharina was eventually imprisoned for 14 months, from 1620 to 1621.
The critical point is that even under the threat of torture, she refused to confess.
That steadfast refusal ultimately led to her acquittal and discharge in October 1621.
This episode just demonstrates the extreme volatility of the era. The greatest scientific mind of his generation had to temporarily abandon his research to prevent his own mother from being tortured and executed.
By local authorities who were likely using the charge to target Kepler's family because of his perceived heresy.
It's astonishing that amidst this chaos, grief, poverty, religious isolation, defending his mother, Kepler managed to achieve what he himself considered his philosophical magnum opus,
Harmonies Mundi.
Harmony of the Worlds, published in 1619.
He had an unshakable conviction that geometrical things have provided the creator with the model for decorating the whole world.
And this work was his attempt to resurrect the ancient concept of musica universalis, aligning the geometrical proportions of the heavenly spheres with musical harmonies.
And it was within this quest for cosmic music, in 1618, while distracted and grieving the death of his daughter Katharina, that he stumbled upon the last of his great laws.
Indeed, he discovered Kepler's third law of planetary motion.
The square of the periodic times are to each other as the cubes of the mean distances.
Or p squared is proportional to a cubed. This simple algebraic relationship is a profound statement. It means that the period of a planet's orbit and its distance from the sun are mathematically linked across the entire solar system.
This law is different from the first two, right? The first two were about the path and speed of one planet.
Whereas the third law connects all the planets into a single, coherent predictive structure.
That's its monumental significance.
Kepler had provided a purely descriptive kinematical framework for the entire solar system. He described how they moved relative to each other, but the underlying reason, the why, remained hidden.
And that law provided one of the cornerstones for future science, particularly for Isaac Newton.
The Newton connection is so powerful. Because Kepler gave us p squared proportional to a cubed, Newton was able to use that relationship to mathematically demonstrate that gravitational attraction must decrease with the square of the distance between two bodies.
The famous inverse square law.
Without Kepler's observation, Newton's force-based theory would have lacked a critical piece of observational support.
So the irony is rich. The law discovered in a theological search for cosmic musical harmony became the mathematical key to a purely physical force that governs the entire universe.
Exactly.
And his mind was so computationally driven during this era that his focus wasn't just on the massive scale of the cosmos, but also on the efficiency of calculation.
Through wine barrels.
Right. In 1613, while in Linz, he observed the rudimentary and often inaccurate method being used to measure the volume of wine barrels.
This need for practical, immediate solutions led him to write Nova Stereometria Doliorum Venariorum,
New stereometry of wine barrels.
in 1615. And his analysis wasn't just about wine barrels. It was an incredibly sophisticated investigation into the volumes of various shaped solids of revolution.
The geometric shapes created by rotating a curve around an axis.
Yes. This work essentially introduced ideas about infinitesimals, the concept of summing up infinitely small slices of a solid to find its total volume.
Which was a significant, crucial precursor to the formal development of integral calculus decades later.
And this isn't just a historical footnote. Today, Simpson's rule, a method used in calculus for numerical integration, is still known in German as Kepler's Faustregel.
Kepler's barrel rule.
It perfectly illustrates how his immediate practical needs, like determining the tax on a barrel of wine, drove fundamental theoretical breakthroughs.
And given the sheer complexity of calculating the Rudolphine tables, he was always looking for shortcuts, which brought him to logarithms.
Yes. When he encountered John Napier's foundational work on logarithms in 1617, he immediately saw its potential to reduce years of calculation to days.
But he was dissatisfied that Napier only presented the logarithmic tables without the full mathematical derivation.
So Kepler developed his own based on arithmetic principles.
And his version, published in 1624 as Chilius Logarithmorum, offered the practical advantage of applying directly to whole numbers, not just trigonometric functions.
Which vastly streamlined the complex computational processes necessary for his primary commission, the astronomical tables.
It's easy to focus only on the laws, but Kepler was arguably the founder of modern optics.
His work in this field stemmed from practical needs, specifically trying to solve the problem of image distortion caused by atmospheric refraction and pinhole camera effects.
During solar and lunar eclipses,
His 1604 treatise, Astronomia Pars Optica, the optical part of astronomy, is rightfully considered the foundation of modern optics.
in it, he systematically described foundational concepts, the principles of reflection, the function of pinhole cameras.
And the first accurate description of the inverse square law governing how light intensity diminishes with distance.
But the real aha moment in that work relates directly to how we see.
Right. Kepler was the first scientist to correctly deduce and state that the image projected by the eye's lens onto the retina is actually inverted and reversed.
This was a huge conceptual leap in the history of neuroscience. Before him, theories of vision were confused.
They often relied on the idea that the image remained upright, or that light somehow carried the upright image directly to the brain. Kepler proved the lens structure meant the image must be upside down.
But if the image is inverted on the retina, why don't we see the world upside down?
Kepler speculated that the visual dilemma was solved by the activity of the soul, correcting the image in the hollows of the brain.
Well, we now know this correction is a function of neurological processing.
He successfully separated the physical mechanism, the retinal projection, from the psychological interpretation, the mind's correction. That separation defined the field.
He also utilized geometry in radical new ways in this work, delving into projective geometry.
He introduced the revolutionary idea of continuous change in geometric shapes. He showed how an ellipse could be continuously transformed into a parabola simply by imagining one focus moving infinitely far away.
And if the two foci of an ellipse merge, it becomes a perfect circle.
He even suggested that a straight line extended to infinity will eventually meet itself, behaving exactly like a massive circle. This notion of a continuum was highly influential in later mathematics.
Then came the telescope. When Galileo published his astounding observations in Sidereus Nuncius in 1610,
The starry messenger.
Kepler responded enthusiastically with his Dissertatio cum Nuncio Siderio, giving Galileo crucial scientific endorsement.
That support was incredibly important. But Kepler didn't stop at endorsement. He launched a theoretical investigation into the lenses themselves,
Which resulted in dioptris in 1611. This is where he detailed the differences between real and virtual images and the function of convex and concave lenses.
And, crucially, he didn't just analyze Galileo's telescope. He improved upon it,
Yes, he described the design for what is now known as the Keplerian telescope.
which uses two convex lenses. Galileo's scope used a convex objective lens and a concave eyepiece, which produced an upright but limited field of view,
And Kepler's all-convex design produced an inverted image.
but dramatically increased the field of view and magnification, establishing the foundation for the modern refracting telescope.
Let's pivot to the fictional side of his mind, somnium, or the dream.
This manuscript circulated around 1611 and was published posthumously in 1634. It's a fantastical trip to the moon.
It's a fascinating piece of literature, often cited as the first true work of science fiction.
Because it blends a narrative story of a young Icelandic boy and his mother traveling to a place called Lavania, the moon, with serious scientific speculation.
Kepler uses the journey to discuss, with scientific rigor, how the Earth would appear to the traveler and what the physics of a non-geocentric perspective would look like.
And tragically, this work of imagination was intimately tied to his mother's trial.
Absolutely. The narrator's mother in Somnium is an Icelandic woman who consults a demon to learn the means of space travel.
And this detail, that she dealt with dark forces to gain secret knowledge, was twisted and used by his accusers to bolster the witchcraft charges against Katharina.
And Kepler, who couldn't bear to leave his scientific reasoning unexplained, later wrote 223 footnotes to the story.
Notes that were several times longer than the text itself.
Just to clarify that the means of space travel described were scientifically theoretical, not magical. He was offending his mother by proving his fictional work was actually celestial physics.
His intellectual breadth was truly staggering. Just one more example. His 1611 pamphlet, Strina sud Denis Hexangula.
A New Year's gift of hexagonal snow.
He wrote it simply as a New Year's gift for a patron. In it, he provided the first detailed scientific description of why snowflakes always exhibit hexagonal symmetry.
And within this tiny pamphlet, he posed what became known as the Kepler conjecture.
A statement about the most efficient arrangement for packing identical spheres into space. This is a fundamental problem in crystallography and geometry,
And it was finally proven rigorously in 2017.
a testament to the enduring depth of a question he posed merely as a holiday curiosity 4 centuries earlier.
And throughout these diversions and crises, Kepler was still bound by his ultimate contractual obligation, the production of the Rudolphine tables.
The monumental definitive star catalog, combining Tycho's precise observations with Kepler's new elliptical physics.
He completed the core manuscript in 1623, but the chaos of the time delayed publication for 4 more years.
Legal squabbles were only part of the problem. The printing process itself was a reflection of the crumbling political stability.
The printing works in Linz were destroyed by fire during the Peasant War of 1626.
So Kepler had to personally organize the relocation of the production to the city of Ulm, overseeing the printing himself.
And when the Rudolphine tables were finally published in 1627, their accuracy revolutionized navigation and future astronomical research.
But the financial struggle never ended. His final years were defined by his efforts to collect the massive debts owed to him by the imperial treasury.
He moved to Sagan, Silesia, serving as an advisor to General Wallenstein, but he felt intellectually and politically isolated there.
Desperate for payment, he set out on a perilous journey to Regensburg in October 1630 to try and collect the outstanding sums.
He fell sick shortly after arriving and died on November 15, 1630, at age 58.
Tragically, he was buried in a Protestant churchyard that was later completely destroyed during the continuing religious conflicts of the 30 Years' War, leaving his final resting place unknown.
Considering the immense depth and precision of Astronomia Nova, it seems incredible that Kepler's laws were not immediately accepted.
We know figures like Galileo and René Descartes completely ignored the work.
So why the dismissal? It seems almost willful ignorance.
The primary reason was conceptual resistance. Most established astronomers objected vehemently to Kepler's introduction of physics into astronomy.
They saw it as mixing disciplines inappropriately.
For centuries, astronomy was a branch of mathematics, a toolkit for calculating positions, to inject forces, magnets, and physical causation. Kepler's celestial physics was just wrong to them.
So they preferred their geometric circles, even if they were inaccurate, because they fit the ancient philosophical boundaries.
Precisely. They preferred elegant, traditional geometric models, even inaccurate ones that required constant fiddling with epicycles, over a physical mechanism that felt messy and unprecedented.
Kepler was literally redefining what astronomy was.
It took the next generation of astronomers to fully appreciate the synthesis.
And the observational proof started coming relatively quickly. His work was put to the test with the planetary transits.
Yes. Pierre Gassendi observed the transit of Mercury in 1631, confirming Kepler's prediction. This was the first ever observation of a Mercury transit.
But the true champion emerged in Jeremiah Horrocks,
Who observed the 1639 Venus transit and became a fervent advocate, correcting and expanding Kepler's work with his own observations.
But the most important vehicle for converting the broader community was that practical textbook.
The epitome of Copernican astronomy. Correct. By the mid-17th century, the epitome had succeeded in winning over astronomers across Europe, firmly establishing elliptical orbits as the baseline for astronomical computation.
It wasn't Astronomia Nova itself, but the accessible textbook summary that cemented his scientific legacy among working astronomers.
Exactly.
And this brings us back to the most critical connection in the history of science: Kepler and Newton.
Kepler provided the data and the geometric description. Newton provided the universal mechanism.
A classic scientific relay. Kepler's 3 laws were the indispensable empirical foundation for Isaac Newton's 1687 Principia Mathematica.
Absolutely. Newton's primary mathematical challenge was solving the Kepler problem, proving that if you assume a universal force of gravity that decreases with the square of the distance, you mathematically derive Kepler's 3 laws.
Kepler described how the planets moved. Newton explained why.
And it solidifies Kepler's place as central to the scientific revolution. He was the intellectual bridge.
Historians view him as the crucial figure who took the tentative geometric heliocentrism of Copernicus and transformed it into a unified, force-governed physical cosmology.
William Whewell, a famous philosopher of science, described Kepler as the archetype of the inductive scientific genius.
And later scholars like Alexandre Koyré emphasized that Kepler's entire system, his mathematics, his aesthetics, his physical ideas, and his deep theology, must be seen as a unified intellectual whole.
Which demonstrates how deeply personal philosophy drove world-changing scientific discovery.
And his influence remains pervasive today. Culturally, we see his impact in the arts.
The German composer Paul Hindemith wrote the opera Die Harmonie der Welt, The Harmony of the World, in 1957.
And Philip Glass created an opera named Kepler in 2009.
And scientifically, he's everywhere. We have Kepler's supernova, his polyhedra, the Kepler conjecture.
And most importantly, for modern times, the Kepler Space Telescope.
That telescope, named in his honor, has observed over 500,000 stars and confirmed thousands of exoplanets in its mission.
So the entire purpose of that program, the systematic, precise search for other worlds orbiting distant suns, is in a way the ultimate fulfillment of Kepler's dream.
His dream of mathematically understanding the universal architecture of the heavens.
So we started this deep dive acknowledging the paradox, and we end by confirming it. Kepler's ability to weave together a deep, almost mystical religious faith, a belief in perfect cosmic geometry, and the harsh demands of empirical data,
Those 8 arc minutes of Tycho's observations.
allowed him to make breakthroughs across astronomy, optics, and mathematics that fundamentally defined the trajectory of modern science.
And let's not forget that Kepler never fully abandoned the astrological framework. He tried to reform it, advocating for the astonishing idea that the Earth itself had a sentient, though not conscious, soul that responded to celestial angles and aspects.
He saw the cosmos as alive, reacting to geometry.
He was the most modern of thinkers, but still deeply rooted in the philosophical magic of his time.
And that fusion of the spiritual quest and the physical law leaves us with our final provocative thought for you to consider.
Kepler's ultimate stated purpose was to reveal God's geometrical plan for the universe through these harmonic proportions.
In doing so, he provided the mathematical keys, the 3 laws that unlocked universal gravitation, a purely physical force discovered by Newton.
So, did the discovery of that powerful underlying scientific law inevitably supersede and replace the theological quest that motivated it?
Or did the physical law merely fulfill Kepler's original, deeply spiritual desire for perfect, elegant truth?
Something to mull over the next time you hear about a new exoplanet discovery by the telescope bearing his name.